Okay. Hello, everyone, and I'm happy to talk to you today. Negative emission technologies are not new, but over the past few years, they've received a very large increase in attention. So why is this? Well, one reason is that the world's doing a lousy job of reducing our greenhouse gas emissions. However, that's not the only reason, and it's not the reason why I became interested in negative emissions technologies. I believe negative emissions have a very important role in helping the world achieve the stated goal of getting to net zero. Uh, a lot of the interest increased when the IPCC put out their special report on global warming of 1.5 degrees C that was released in 2018. This is a graph from the summary for policymakers, and it shows some of the key elements to understand when we're talking about negative emissions. This is just one scenario of trying to meet a 1.5 degrees C target. Um, and the different colors mean different things. The gray are the greenhouse gas emissions that are coming off. The brown is the agriculture, forestry, and other land uses that either can release CO2 or they can become a sink for the CO2. And in this case, they're using bioenergy and carbon capture and storage, which is in the yellow, as a major negative emissions technology in showing what happens here. Over time, the emissions reduce and the negative emissions technologies increase, and eventually we'll reach net zero, and that's where uh, the amount of CO2 being emitted will equal the amount of CO2 being removed from the atmosphere. As we continue on, we can even go net negative if we want to pay for it and if it's required. So this is sort of sets some of the terms that we'll be using as we move forwards. The number of studies and articles on negative emissions has really increased quite a bit in the past few years. And an example of two of these studies, these are from the United States government, one in 2015 from the National Research Council and one in 2018 from the National Academies. One thing to note is people refer to negative emissions as different things. So in 2015, this was called carbon dioxide removal, which is still used. So it's different than carbon dioxide capture, which I do a lot. Carbon dioxide capture refers to taking carbon dioxide out of exhaust streams like smokestacks of power plants. Carbon dioxide removal usually refers to taking it out of the atmosphere. Uh, the term negative emission technology has become more popular and is used quite a bit. Once again, negative emissions technology are just the technologies you use to remove carbon dioxide from the atmosphere. I've been around a while, and in the old days, we just called these things offsets. And I still like the term offsets because it has a certain connotation, as we'll talk about in a moment. But another new term that has come up has been net zero. And at first, it sort of tried to discern between going from absolute zero, saying absolute zero emissions. Well, maybe we can have some emissions and we can offset those and just become net zero. And that, of course, has taken over a lot of the talk. And as we see in a lot of the Paris, the what countries pledge for the Paris Accord is to get to net zero by a certain time. So that all seems interesting, but recently there have been quite a few articles that have really made net zero a bit of a lightning rod, and people are questioning, is that the right term? But I'll tell you where I'm coming from. I'm an engineer, and one of the first things they teach engineers is how to do a simple mass balance. And a simple mass balance is in minus out equals accumulation. If we go back to the Framework Convention on Climate Change, where started all the international protocols to try to get to reduce it, and it's been ratified even by the United States and the United States Senate. Uh, the Framework Convention calls for stabilization. Specifically, its stated objective is to stabilize greenhouse gas concentrations in the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. Well, what does stabilization mean? Stabilization simply means that the accumulation of greenhouse gas in the atmosphere will become zero. Um, well, what about net zero? It basically says the same thing, but on the other side of the equation. It says that in minus out must equal zero. So, really, in some ways, there's nothing new here except the terminology and how people use it. So, let's explore this a little more. And here um, is the role of offsets or negative emissions in getting us to net zero. And what this means is what it means if we use these to offset expensive areas to mitigate, that means this could be economically beneficial. So if say mitigating CO2 emissions from an airplane may cost maybe $500 a ton of CO2, say. Well, if I have negative emissions that are $100 or $200 per ton of CO2, uh, it's better to use those to offsets, and then we can leave the airplane working just as they are today. Uh, so this makes economic sense. And how much of these emissions do we need? This is something from Science magazine a number of years ago that talks about what are difficult to eliminate emissions, also expensive to eliminate, and they identified maybe about 30% of our emissions are in that category. And when we add in other difficult emissions outside of the energy sector, such as agriculture, this number could rise even more. Now, we don't need negative emissions to offset all of these. There's other things we can do, such as in load following electricity. Maybe we can use hydrogen and cement and iron and steel, carbon capture and storage from their smokestacks may be worth it. But they're probably still going to be a few gigatons, 1, 2, 3, 4. Now, we don't really know. They're going to be really hard to offset, and that negative emissions could be very important to do this. Now, on the other hand, if we want to use these technologies to go net negative, I think it means a very different thing. Why would we do this? Because we want to meet a stabilization target that we overshot. So say we want to hit a 2 degrees C stabilization target, but we're already at 2.5 degrees C. The only way we can get back to that other target is to start taking more CO2 out of the atmosphere than we put in. In other words, going net negative. This has a couple implications. First, we're going to need probably a lot more of these negative emissions than we do to just offset, probably on the order of tens of billions of tons of CO2 a year. Secondly, the cost is going to be much greater than today's mitigation cost. So why that's important? Think of what we're doing. Today, maybe we can mitigate for $10, $20, $30 a ton of CO2. The European trading system, their carbon market's up maybe close to around $50 a ton of CO2 today. So we can do mitigation on the tens of dollars per ton of CO2 today. But these negative emissions, they're cost more, and a lot of them will cost in the hundreds of dollars per ton of CO2 today. So because we won't pay the cheaper price today, we're going to say our children and our grandchildren and their children will pay even more in the future to remove what we should not have put in the atmosphere. There's some moral issues with that I won't go into, but it's not a very good argument to go net negative. The other thing is just psychologically, if we're not paying the cheap price today, what gives us any thought that future generations will be that so much different from us that they'll even pay more to clean up our mess? It doesn't quite make sense to me that this big push that we need these negative emission technologies just to clean up and overshoot is the main reason to move forward. So let me summarize here. There's some very hard, bordering on impossible emissions to get out, and we're going to need to offset those with negative emissions. And I think that makes a lot of sense. It makes economic sense to achieve stated goals we have in place today. However, I'm not so sure of getting to net negative, but I think discussing it is a real total distraction. Why do I think that? First, we can't even get to net negative without getting to net zero first. Since it's important to develop these technologies to get to net zero, we're going to develop them anyways, and getting to net zero is a good enough reason. Secondly, we don't have a lot of information. A few decades down the road, when we're approaching net zero, we have a lot more information on these technologies, uh, their benefits, also the negative sides of them. And at that point, they can make an informed decision on whether to proceed to net negative. So, what are these technologies? There's lots of ways to look at them and view them. This is something I made a couple years ago. I think what's interesting, it shows that there's a variety of mechanisms to remove the CO2 from the atmosphere. A lot of these are biological, and there'll be a lot of the focus we have over the next 2 days in the symposium. Some are chemical or geochemical, and there's lots of different storage mediums that have been proposed. The terrestrial biosphere, which is our soils and vegetation, is a big potential sink. Um, the ocean has been talked about as a sink, and both of these are natural sinks also. So a lot of this is enhancing these natural sinks. They talk about putting it into rocks through weathering, which is the way nature takes care of a lot of the CO2, but it does that over time scales of hundreds of thousands of years. So that would have to be speeded up. And of course, the deep geologic formations, the same type of formations we use with regular um, carbon capture and storage. I've worked on a few of these technologies besides the bioenergy with CCS. So I'll say a couple words about them. Each of these technologies have different opportunities, but also different challenges. None are a slam dunk. And in fact, I think some are non-starters. And one non-starter, I think, should be iron fertilization. It's always on everybody's list. Uh, I was in a project about 20 years ago. The Department of Energy had a little center out at Berkeley on ocean carbon sequestration, which I took part in. And part of that was direct injection in the ocean, which is what I was interested in. But other people who were there on the iron fertilization, I learned a lot about it. And what I learned was that in order for iron fertilization to work, you have to really change the ecosystem and the biology in the ocean, um, from the photoplankton. You have the Noxia in the ocean, and the environmental impacts were so great that I became convinced it was a non-starter, not just from an environmental viewpoint, but from a political viewpoint, that it will never get going. But it keeps coming back. It keeps coming back, and it's always on these lists. So one has to be careful. The other one I did a lot of work in more recently is direct air capture, analyzing it. And there's a lot of numbers out there, and numbers of $100 to $300 per ton of CO2 has become very common in the literature. And I just cannot see those numbers as being credible. The work that I've done said these numbers are more like $1,000 per ton of CO2. And even though the numbers can come down, because CO2 is so dilute in the atmosphere, trying to run systems like carbon capture and storage systems we do on the smokestacks are just going to be very much more expensive for some very sound physical reasons. But today, we're going to focus on bioenergy with CCS. Rob and Bob gave a good introduction of exactly what this means, so I won't do that here, but I'll proceed to the next slide and say that even though there's a lot of good potential in these negative emissions technologies, there has been pushback lately. There was quite a few articles. This is one article I saw recently on March 3rd from The Guardian, and it says that the climate crisis can't be solved by carbon accounting tricks. And it brings up some realistic areas we need to be careful about when we work with negative emissions. One talks about one complaint is the unrealistic over-reliance on carbon removal to preserve the status quo. And this comes from a lot of the integrative assessment models using negative emissions technologies to meet the very hard to meet stabilization targets of either 1.5 or 2 degrees C. And we see a lot of negative emissions coming in versus mitigation, and that leads people to say, oh, maybe we don't have to mitigate so much, but we should uh, just go to these emissions. And I think that's not the right way to look at it. You got to look at both these negative emissions as helping in the mitigation campaign, not saying we have to do less mitigation. We have to just as much mitigation whether we have whether we have this available or not. But maybe we can save the cost on some very difficult to mitigate technologies. The second is not getting what you think you're paying for in the self-regulated carbon market. And this is something that I think is real, and we see some problems in some of the negative emissions, especially some of the forestation, reforestation projects already. But this is something that I think can be taken care of. So when we look at the negative emissions and we do the accounting, we have to make sure on some of these, some of the afforestation projects, you need a baseline. So you have to say, what's the baseline? Is that a correct baseline? And in just a moment, I'll give an example of how that can really get us messed up. Secondly, you have to make sure you do a good life cycle analysis and take into account all the carbon footprint of the full life cycle of this, and only count the net removal, not the gross removal from the atmosphere. Uh, and when you're looking at biological type of removal mechanisms, you always have to be aware of land use changes and what the implications of that, whether they're direct land use change emissions or indirect land use change emissions, which are not always easy to calculate. What I want to just show here is something that was in the Boston Globe, my local paper, just a month ago. And it's about the Massachusetts Audubon Society, which I'm a member of. They have a lot of nice nature preserves around the state, a lot of forest on them, among other types of nature. And, they never, I don't think, ever had any intention of harvesting trees from their nature preserves. Is sort of not what they do, not what they sell their members on. Yet it's so California on saying, well, we can cut down all these trees, but we won't if you give us some money and give us some carbon credit, and we'll give you some carbon credits. So they gave the state of California 600,000 carbon credits. State of California gave them $6 million, and they say we're not going to cut down our trees, which this article said basically, well, they weren't going to cut down the trees anyways. So this is something that in this type of world they call additionality, that just wasn't taken into account, right? But this isn't the only example. There was a related story that says up to 39 million carbon credits that the state of California gave out. Once again, were not real credits. They were giving people credits for things that they were going to do anyways. I have a bunch of trees in my backyard, but no one's going to pay me not to cut them down. Or at least I don't think anybody is. So getting back to bioenergy and CCS, and to sort of set up the rest of today and tomorrow, in the bioenergy area, there's lots of feedstocks we can use. You can use energy crops. You can use residues from sawmills, from pulp and paper. You can do agricultural residues. People have talked about using municipal solid waste as your biomass source. And you can make many products, electricity, hydrogen, liquid fuels, biochar. Some of the problems with the liquid fuels like biodiesel or methanol is they contain carbon. So even if you capture CO2 emissions during the conversion of biomass to these fuels, will you capture enough CO2 that the whole process will be carbon negative, and you have negative emissions? A lot of these will be closer to negative carbon neutral. One liquid fuel you can do is ammonia, which is similar to hydrogen, as a hydrogen carrier. Hydrogen, once again, is a carbon-free energy carrier like electricity. One of the problems today with hydrogen is we don't have the infrastructure built up for this energy carrier as we do with electricity. So at this workshop, we're going to primarily focus on uh, energy crops, because if we're going to do this on a large scale, we're going to probably have to go beyond residues. And the primary projects we're going to look at is electricity. Some of the talks will go beyond this and talk about some of these other issues, but with the paper that Jen's going to present in the next talk, uh, it will be primarily looking at energy crops going into electricity. So I think we have a great webinar, a great symposium today. As I said, the next talk's going to be a paper that I collaborated on the economics of bioenergy and CCS in a carbon-strained world. And it'll be insight from our integrated assessment model that we have here at MIT EPA. The next session is going to look at the biomass supply chain. We have a great set of experts lined up for that. They'll look at issues like biomass availability, life cycle emissions, measuring, monitoring, verifying the environmental impacts, land productivity, and how that may improve. The third session is going to talk about the bioenergy and CCS components in action, biomass power plants with carbon capture. We'll give a great update from a colleague I've known for a long time, Sue Hovorka, on what the latest status is on storing CO2 in geologic formations. Another co-author of our paper, Matilda Faraday, is going to talk about some of the system issues involved in these BECCS projects. And finally, we'll end with policy issues. And as I say, there's a lot of policy issues going on. We'll talk about the role of bioenergy and CCS getting to net zero, the problem of scale, impacts on global food system, government issues, infrastructure needs, and also, very important, how do we move forward in doing this? So there's a lot of possibilities for bioenergy, CCS. There's a lot of challenges, and we just hope to explore these and get them on the table over the next 2 days. So with that, I'll stop and I'll turn it over to Jen.